Recently, various companies have been experimenting with putting massive data centers under the ocean. On the surface, this seems like a pretty dumb idea. Computers and seawater? However, there are actually some legitimate benefits, namely that being surrounded by water allows for rapid dissipation of heat, which has got me thinking, is it possible to do something like this with normal PC hardware?
Well, to find out, I've got some of the most power-hungry PC components available right now. An RTX 4090 and an Intel i9-13900K. At full bore, these components kick out an insane amount of heat, totaling over 800 watts. This is enough to bring the temperature of a room up several degrees in just an hour, as it's basically a mini space heater at this point. When things are scaled up to the size of a data center, generating many thousands of times more heat than this setup, you can imagine how wild the cooling has to be for them, and the idea of putting them underwater isn't actually as silly as it first sounds. But keeping hardware dry is no easy task, as I found out in my submarine project, which had leaks and buoyancy issues. The concept of encasing all the hardware inside a clear acrylic cylinder, though, is worth experimenting with, as it's a strong shape that only requires end caps to become watertight. The acrylic cylinder I've bought this time is way larger, but even so, it's only just big enough to fit over the main components. To make it watertight, my plan is to make some end caps that can be used alongside some sort of gasket material to make a watertight seal at each end. As acrylic is a poor conductor of heat though, it essentially insulates the system from any surrounding water, locking in heat. So to allow this heat to be quickly dissipated, my plan is to build a sealed internal water cooling loop that can transfer heat from the components inside to some external copper pipes, which can in turn be kept cool by the surrounding water. Being a sealed loop with its own pure coolant means that the delicate heat transfer blocks that cool the components themselves will be protected from external contaminants like silt and algae, but it should still allow heat to be quickly and efficiently removed thanks to the copper pipes being kept cool at all times. To make these copper pipes into a frame, I'm using the end caps themselves as a base by carefully drilling a ring of holes that are just big enough for the pipes to fit through. As you can see, these caps are actually made out of copper as well, and the reason for this is because it allows me to solder standard brass or copper plumbing fittings directly to them, making reliable watertight seals around everything, vital for protecting the components against water leaks. I am of course using lead-free solder here to avoid any environmental contamination when it's all finished and in use, and much respect to the professional plumbers out there that can actually make lovely looking solder joints, unlike mine. It really is super hard to do neatly. Still, after a cleanup process involving wire wool and metal polish, followed by a thorough wash, the cooling frame has ended up looking pretty cool, with a mid-century industrial character to it. I have a feeling this is going to look pretty amazing when it's sent underwater, but how is the acrylic going to be mounted to this in a watertight fashion? Well, behind every copper pipe, there's a hole for attaching some threaded brass pillars. These are for holding some threaded rods, and the idea behind them is to use them almost like a ratchet system to pull both caps together, squeezing the acrylic cylinder in the middle. As there will be a simple rubber gasket between the caps and the acrylic, this pressure will hopefully be enough to keep the thing watertight, but we'll have to wait until later to test this out. For now though, we need to start working on the system for the inside. As I mentioned earlier, the individual components for this are some of the highest end parts available right now, most of which have been provided by the manufacturers for this build, including the graphics card, a Zotac RTX 4090. It's extremely powerful, capable of drawing 450 watts on its own. Great for gaming of course, but particularly useful here as the high power consumption means that we'll be able to push as much heat as possible into our cooling system to see just how capable it is. And it'll need to be. Load testing these parts together pushes them to draw over 800 watts, which is kind of insane for a single PC. And it gets hot, with the CPU thermal throttling itself at 100 degrees Celsius on an air cooler. Yikes. Better cooling is sorely needed. Now to power all of this, I'm using a 1000 watt Seasonic power supply. This is particularly useful for the build because it has extremely efficient internal voltage regulation, which means that it will barely contribute any heat to the inside of the chamber, but more on why this is important later. To mount everything together, I'm building directly onto the PSU's frame using right-angle brass links to give me some mounting points for the rest of the components. This open frame concept makes adding everything else a breeze, and as some of you might have noticed, EK Waterblock have provided a variety of water cooling parts so that we can use flowing water to rapidly pull heat away from the processor and graphics card to transfer it to the copper pipes. All of this needs to be super compact to actually fit inside the cylinder, and there's just enough room for the reservoir at the front. To finish things off are 3 of Crucial's blazingly fast T700 SSDs. These can mount directly onto the motherboard, and as they are 4TB each, it gives the system 12TB of internal storage, perfect for a mini, ultra-fast underwater data server, striking at the core of what this whole project is about experimenting with. So, with the system now complete, it can be lowered into the cooling frame and hooked up to the copper pipes so it can dump any heat it generates into them. I'm using some quick release adapters for this so that the system won't need draining if it ever needs to be accessed for maintenance. For longevity though, it would of course be best to add a biocide to its coolant, but as I want to test the system in a freshwater habitat, I don't want to run the risk of any chemicals ever leaking out and contaminating things, so I'm just using pure distilled water, so it's nice and environmentally safe. For the watertight seal, I was originally just going to use rubber O-rings, but as the acrylic cylinder is only 5mm thick, keeping them centered is a bit problematic. So I've decided to cut some much wider custom gaskets out of rubber sheeting, which look more hopeful. I mean, it's not like these are the only thing between the water and thousands of dollars worth of computer hardware or anything, right? In an effort to further reduce the chances of leaking, the edges of the acrylic, which are rough cut, need to be sanded down. I've ended up on a pretty fine grit value for this, which takes it pretty close to being shiny, but in a somewhat risky move, giving it a blast of heat takes it to that final level of polish. Despite all the new components, the acrylic tube can still just fit over everything. Phew. As for the top cap, I've decided to add a long tube through its centre, flanked by handles on either side to make it easy to carry. This tube will give all of the power and data wires a path to air without having to worry about making them watertight, as its end can sit just above the surface of the water. Now, some of you might be wondering why I've also added a heatsink to the underside of this cap. Well, it's for cooling the air inside the chamber, as there'll be undoubtedly some heat introduced to it by components that aren't hooked up directly to the water cooling loop, such as the power supply, so it's quite an essential component. And with that, the threaded rods can be tightened up, clamping the whole system together. And what a stunning system it is! The copper pipes give it a real retro vibe, and that they have a thermodynamic reason for being there rather than just for aesthetics makes it all the more authentic. And as we've got a clear central column that houses the components, I thought that it would be a good idea to add some internal illumination for when it's turned on. Are you ready? Whoa! Honestly, this is one of the coolest looking things I've ever built, and I love the combination of the warm internal lighting and the polished copper. All the hours spent cutting, soldering, polishing and designing have been well worth it, and this is quite possibly one of the most unique PCs in the world. Aesthetics aside, it does have a job to do, however, which is keeping the internal hardware not only dry, but cool as well. So it's going to be really interesting sending this incredible build underwater to see what kind of thermals we get, assuming it doesn't leak, of course. But before we get to that, also in search of incredible are ASUS, who have sent over their Zenbook Pro 14 Duo OLED for this sponsored ad segment. Opening it up, we can clearly see that it's no ordinary laptop. Its secondary display, being an extension of the main desktop, is incredibly useful for productivity as windows and apps can be pushed to it. This is great for referencing and CAD work, and it can be genuinely helpful when you're working on various projects, even submersible PCs. Complementing this secondary screen is of course the main display, which is a high refresh rate ASUS Lumina OLED panel that has a 100% DCI-P3 colour gamut for accurate colour reproduction and a blazingly fast 0.2 millisecond response time. Being OLED, it of course has inky dark blacks, which makes content incredibly pleasing to the eye for both colour critical creative work and well-earned movie breaks. This is the first laptop that I've tested that I actually like using for work, and it passing military-grade durability tests such as extensive shock testing, vibration testing, and of course temperature and humidity testing ensures that it'll be a reliable workhorse in real-life working conditions for years to come. A laptop that pushes the boundaries of design like this is in itself inspirational, as conceptualizing ideas is a fundamental part of building incredible things, for those who are in search of incredible. And if you yourself are in search of incredible, you can check out the ASUS Zenbook Pro 14 Duo OLED by clicking the link in the description below. Now, a primary consideration when you build anything that goes underwater is of course its buoyancy. Now, I found out this the hard way when I built my DIY submarine project, as I made it far too buoyant and had to weigh it down a lot to get it to go underneath the surface. So to avoid that same issue this time, let's calculate it. You see, an object's buoyancy is simply defined by whether its weight is lighter or heavier than the volume of water that it displaces. As our central cylinder displaces approximately 24.5 kilograms of water, the whole thing needs to weigh more than this in order to sink, which handily it does, by a mere 100 grams. But there's a catch. Some of this weight exists outside of the central cylinder by way of the copper pipes, which contain about 2.4 litres of water, throwing off our weight measurement. Subtracting this from our final figure indicates that we need to add a bit of extra weight to compensate, so I'm going with 2.5 kilograms of steel pellets inside bags to make it slightly negatively buoyant. So the time has come to send this under the water. Will it sink? Obviously it will sink, we've calculated that, but will it leak? I'm not sure. Let's find out. Rather than submerging it into the sea, which would be very risky, I'm giving it its first tests in a garden pond. Despite appearances, this small body of water is extremely deep, well over 2 meters, or 7 feet. This depth makes it ideal for testing the PC in, with the added benefit of it being somewhat of a controlled environment. As you can see, it's teeming with life, which is why it was so necessary to ensure that the PC itself would be benign to its environment and non-toxic, and it's going to be interesting to see what the fish make of it. After giving the system a final check to make sure all the bolts are tight and that there are no obvious problems, it's time for the moment of truth. In an effort to have a quick mission abort option, I thought it would be a good idea to set up a rope and pulley system so that I can quickly remove the PC from the water if I detect any water ingress. Right, so we've got it all ready to go over the pond, so hopefully this goes well, and then we'll lower it in and just monitor whether we have any leaks. I'm a bit nervous. Remember, there's over $5,000 worth of computer hardware inside this acrylic cylinder, and the only thing keeping it dry are 2 homemade rubber gaskets. No pressure then. As it's lowered into the water, my heart is pounding, but so far, so good. With it almost entirely submerged, it's time for a quick leak check, and thankfully it's bone dry. The gasket system works perfectly, and I'm starting to think that this might actually work. But there is a small problem. It's actually still positively buoyant, despite my calculations. Experimenting with some external weights reveals that it requires an extra kilogram. How did I get my calculations so wrong? Well, I forgot to take into account the fact that all of the external components, the handles, the walls of the copper pipes, and even the end caps themselves, do of course displace water as well. And although each part is individually heavier than the water that they displace, they need to be treated as part of a whole. And indeed, after including this in my sum, it now marries up to the requirement of an extra kilogram. Thankfully though, this is easily countered by adding some more steel weights, so we should be good to go.
Right, so we've got it underwater and everything so far is looking really promising. I'm not seeing any bubbles coming up, which is a good sign, and it is just negatively buoyant. So that's why the rope is just holding it up, just so that the top bit doesn't go too far under the water. But you might be wondering how on earth we're going to turn this on, and also how are we going to plug in things like the monitor and keyboard and mouse and stuff? Well, everything is actually going to be running through this Thunderbolt cable. This is 50 meters, and the reason why it can be so long is because it's an optical one. It was very expensive to get, but I thought it was worth it for this video.
The other end of this Thunderbolt cable can simply be plugged into a little dock, which gives me various monitor outputs, USB ports and audio outputs, everything that's required to operate a PC, apart from the mains power.
Okay, no explosion, so that's a good sign. So I've got the power button here. So 3, 2, 1. Whee! Look at that! Okay, so I'm not sure if we'll get a signal yet. Oh, there we go! Look at that! We've got an underwater PC. Check this out. I'm just having a look at the onboard camera. Yeah, it looks dry in there. I'm not seeing any leaking. So now it's time to do some thermal tests and see just how capable this cooling system is and whether it was worth the effort.
Launching Prime 95 and Thermark together pushes the system to draw the familiar 800 watts as expected. With the pond itself being about 17.5 Celsius, the starting coolant temperature being just above this doesn't seem particularly amazing. But what is amazing is that it barely goes up from this, with a maximum reported coolant temperature of just 20.8 Celsius after about an hour. A temperature delta of just over 3 degrees Celsius is very impressive, and it shows that the cooling system itself is very capable at transferring heat, resulting in a CPU temperature that instantly flatlines at 60 Celsius and a GPU that flatlines at 41 Celsius, refusing to go any higher. Even the internal air temperature, which remember is only being cooled by a small heatsink, keeps at a moderate 28 degrees. Not bad at all.
That the PC is able to dump its heat so quickly into the surrounding water really is a good indicator of how capable the cooling system is. And I'd say we're only just scratching the surface of what it's actually capable of cooling.
As the pond experiences zonal temperatures up to 25 Celsius in the sun, I doubt that the mildly warm copper pipes will pose a particular hazard to the wildlife. And as there's so much water in contact with ground soil, it's also unlikely that the PC will ever add a degree to the pond's total temperature, as the soil will help to dissipate it. Now, one minor change worth making is adding some rings of foam around its pole. This allows the pulleys and ropes to be retired as the system is now free floating, with the slight negative buoyancy keeping it just under the surface, with the foam rings preventing it from sinking any further. I can't quite believe that it's all come together and works so well, and it feels great to have it independently floating now. Remember, these are some of the most power-hungry PC components available right now, and the i9-13900K being kept at 60 Celsius is actually quite impressive considering how much power it uses, with the bottleneck being its thermal interface material rather than the cooling system itself.
So really, mission accomplished. We've successfully built a PC that can use surrounding water to keep itself cool. Now it's time to have some fun. Here we go! Halo Infinite on a submersible PC. Let's go! I can barely see the screen now because of the sun. Still, pretty cool. So having an underwater PC certainly is a novelty, but why on earth are companies experimenting with having underwater computers or data centers at all?
Well, besides the significant cooling advantages, some other benefits are quick deployment for coastal regions, and the sealed environment that the internal chamber provides can keep hardware in optimal conditions for longevity. I'd imagine that the EMP protection that water provides is something to be considered here as well, especially in the event of some kind of geomagnetic storm from a solar flare. Having a data backup at the bottom of even just a pond would provide significant protection against this. Regardless of any real-world advantages though, a submersible PC is just plain awesome, and who knows where the idea can go from here.
So, I hope you've enjoyed this journey of discovery building a submersible PC. If you like all these kind of weird projects, then don't forget to subscribe. But other than that, I'm Matt, you've been watching DIY Perks, and I hope to see you next time. Goodbye for now. Off she goes. So cool.